A sequence is an infinitely long list of real numbers. So here's a common example of a sequence. I could write all the even numbers. Eventually I get bored of this though, so I'll just put dot 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 to represent the rest of them. This is the sequence of even positive integers in order from lesser to greater. And we're going to find lots of different applications for sequences in calculus. So just as an example, we could do this problem right here. We'll have to use our intuition because there's not a unique answer here, but there's some obvious choices for what we should pick for this problem. We're going to use our intuition to guess the next three terms of each of these sequences. Okay, so for this sequence right here, 1, 3, 5, 7, 9, using our intuition, we can guess that, well, this is obviously talking about the odd numbers in order. So the next odd number, in fact, I'll just write out the entire sequence. 1, 3, 5, 7, 9, and I have to guess three terms there. So the next term would be 11, 13, and 15. And that would be the next few terms of that sequence. Okay, let's do the second sequence here. Looks like we have 3, 6, 9, 12. I'm ignoring the negative for now. But we have 3, negative 6, 9, negative 12, 15. And so we have two things going on here. We've got positive, negative, positive, negative, positive. So if we're using our intuition, we should know that the next one will be negative. And it looks like we're adding 3 each time to the positive number part. Or I guess I could think of this another way. These are multiples of 3. 3 times 1, 3 times negative 2, 3 times 3, 3 times negative 4, so on and so forth. So positive, negative, positive 21, negative 24, and those are my three new ones. Here are my three new ones up here. Let's do the last one. 0, 1, 4, 9, 16. And again, there are many sequences that start with the same numbers, but the one that makes sense, the one that we were probably talking about here, if we just recognize what these numbers are, 0, 1, 4, 9, 16, those are all, they're squares, right? They're square numbers. And so the next square number, this is 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. So 5 squared is 25. Then 6 squared would be 36. 7 squared would be 49. And then 8 would get 64, and 81, and 100, and so on and so forth. But that's it. Those are the next terms in the sequence right here, 25, 36, and 49. Good deal. All right, so we have to have some intuition for sequences if all we're given are just the first few terms, and we're just guessing. There's no reason that the sequence couldn't have different terms following, but this is just a bit of common sense of what the person's probably trying to describe. So we want to be able to describe things exactly. All right, so let's see. To describe things exactly, what we're going to need is a formula for the sequence, and so we'll talk about two kinds of formulas. Let's start with explicit formulas. And an explicit formula is given by, usually in this format, some letter like A or B or C, whatever, with a subscript, usually the letter N, maybe sometimes I or K is used there. But what this tells us is that this is the term N of the sequence, where terms are the different numbers within the sequence. All right, and then it's going to be given to us as some function of the number n. We call this n. N is the index right there. So a sub n is the term, the n is the index of that term, and the explicit formula is just some function of n. For example, maybe it's 4 times n plus 7, for example. All right, it's just some sort of function. It could have an n squared. It could be sine of n. We could have e to the n. We could have all sorts of things. Anything like we were used to dealing with functions, we just have n instead of an x. And in this case, n is some positive number. That's one of our indices for the sequence. Okay, the question then is, well, where do we start with the index? And that's why we have to be given a start. And the assumption is that it depends on who you're asking what the default is. I use 0 as the default starting point for the sequence. So this is a way to write the entire, so if this is the formula for the sequence, then the sequence itself, you have the angle brackets around it. This tells you to start at n is equal to 0 and keep going to infinity, and it would spit out a0, a1, a2, a3, dot, 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 so on and so forth, where each of these are what we get when we plug in to the function. So for example, if 4n plus 7 is our function, then we get 4,0 plus 7, 4,1 plus 7, 4,2 plus 7, and we start by plugging in 0 because we were told to right there. So that gives me what? 0 plus 7, 4 plus 7, 8 plus 7, so on and so forth. You can kind of see how we're adding 4 each time, so I already know it's going to be 19 and then 23 if you want to add a few more terms in there. Okay, and if we have an explicit formula, it's very easy to come up with a graph. Remember, the formula is, in our example, if it's 4n plus 7, then we can simply, we know that we're starting by plugging in n is equal to 0, so I'll get a different color here. At 0, we got 7, so that was, again, that was a0 here is 7, so at 0 we got 1, 2, 3, 4, 5, 6, 7. At 1, we go up to 11, so 7, 8, 9, 10, 11. The second term, we go up to 15, 1, 2, 3, 4 more, and then at 3 we go to 19, 4 would go to 23, and we keep on going, but we don't connect the dots. Even though it keeps on going and going and going, we don't connect the dots because in a sequence, nothing exists between these numbers. There are no fractions allowed to be plugged into a sequence because it's just a list of numbers starting with usually 0, although if it was a 1, then we would just scratch this part out. We would start with 11 instead. But we just have a list of numbers and we can graph them just like we graph a function if we would like to. All right, let's take a look at a couple of examples involving these explicit formulas. So there's an example problem. We're given 3 explicit formulas, and we're told to write out the first few terms of each sequence. So let's start with an. Okay, we've got an is equal to 4n. So an, where n starts at 0, because we're told it starts at 0 right here, up to infinity, that would be a0, a1, a2, a3, a4. We can stop there because we included the 0 term, and that gets us 1, 2, 3, 4, 5. And now we're going to plug into the formula for an. An is given to us as 4 times n. So this is 4 times 0, 4 times 1, 4 times 2, 4 times 3, 4 times 4. All right, and then doing this an term here, that gets us 0, 4, 8, 12, 16, so on and so forth. All right, that's all there is to do there. Okay, for bn, we are also going to start at 0. We're given this formula, so it's a little more complicated. So bn from 0 to infinity. All right, we'll start with b0, so we get negative 1 to the 0 over 0 squared plus 2. Negative 1 to the 1 over 1 squared plus 2. Negative 1 squared, 2 squared plus 2. negative 1 cubed, 3 squared plus 2, negative 1 to the fourth over 4 squared plus 2, so on and so forth. All right, let's evaluate each of these. So if it's negative's got an even power, it just does nothing. It becomes positive 1. These other ones are going to become negative, though. So we'll have alternating positives and negatives. And let's make a note here that negative 1 to the n thing up here causes alternating positive and negatives. And that's a very common pattern that we see in sequences. All right, let's compute the rest of these numbers. We've got 1 over 2. Okay, we've got negative 1 over 1 plus 2 is 3. We got positive 1 over 4 plus 2 is 6. Negative, because of that odd power here, negative 1 over 9 plus 2 is 11. Positive 1 over 16 plus 2 is 18. And this is a good example of a problem where it's not really obvious at all where the formula came from, but it's really easy to use the formula to get the terms of the sequence. Okay, for the last one, we've got this cosine thing here for the C term. I'll do that in green. So again, we're starting at 0, and it's given by cosine of pi over 2n. So Cn from 0 to infinity will get us cosine pi over 2 times 0, cosine pi over 2 times 1, cosine pi over 2 times 3, times 2, now 3, 4, and that's 5 total at that point. All right, so what are we looking for? Cosine of 0, cosine of pi over 2, cosine of pi, cosine of 3 pi over 2, and cosine of 2 pi. And that gets us 1, 0, negative 1, 0 again, and 1. You can kind of see actually this pattern would keep continuing because we keep rotating around the unit circles. So the next term, if we were to add more terms, we'd get another 0, another negative 1, 0, 1, 0, negative 1. I could keep on going, but I didn't have to. I could stop at the first 5 terms. All right, let's just do one more example. We've kind of been doing this, but what if we're just asked to give a term for a sequence defined by a particular formula? Well, that's just a matter of plugging in. It's just sort of like a function. It's basically what we just did a moment ago. But here we don't have to list out all the terms. We're just told to give me the 7th term. And so whether we start at 0 or 1 or some other number, it doesn't matter. We just replace all of our n's with 7. So we got 7 over 2 times 7 plus 1. 7 over 14 plus 1 is 7/15. So that's really all there is to it, is plugging in, just like we would plug into a function, but for sequences we're only allowed to plug in integers, whole numbers.